Hi everyone, I'm Tara Javidi. I am the Jersey Lowak Endowed Chair Professor of Electrical and Computer Engineering, as well as with a joint appointment in Hallett-Yoklu Data Science Institute. I'm going to talk about the future of AI systems, and in particular, my work on how to incorporate curiosity in these future systems. As we go, I'm going to give more credit to folks who have helped me along, but I just want to say that most of the research part of the questions are work that I've done at UCSD with my PhD students, and then implementation and turning it into a product to bring it to the market is work that I've done with the team at Cov AI, the startup that I have co-founded. So when we think of intelligence, we think of it as innately coupled with curiosity. The ability to actively go out and seek out information that you need to make sense of the world through our senses. This is vastly different from the current AI systems that really are built on training and learning from vast amount of data that is passively collected and ingested into building these intelligent systems, quote unquote. So what I want to talk about is why is that there is such a big difference between the way we think of intelligence in the nature, as I was showing you in these sets of videos, and how our current AI systems are really built. Why is that when we think of humans, we don't think of the ones who just sit in front of something hoping for the data to arrive to passively become smart as necessarily that intelligent. We don't think that's sufficient. Processing data is not enough. We think of them as intelligent if they go out and seek out the kind of information that they have. And this applies to other creatures in the nature. So let me just try to understand the process of sensing, or the physics of sensing in the real physical world. The process of sensing really comes in this sort of, I'm showing you the two extreme. It's really caricature of what you see in real world, but it's meant to really depict what we see. On the one extreme, on the top part, on this top part, I'm showing you data that can be collected if you take a sensor really close to a target of interest and see the details. So for example, see here, you see that this fellow has removed his hard hat. On the other extreme, I'm showing you images you would collect if you move away the camera, the sensor, away from the target. Now you can capture the context. You cover the whole site. You see the crane, the larger context that can cause safety violations, but the details are missing. You don't see if this person is protected enough. In fact, there is a sort of a trade-off that you will see, and that's what I call a physics of sensing, that is true for any sensors. Of course, I'm just showing you here these images, these cartoon images and camera depictions, but the same thing is true for any sensors. There is this trade-off as the detail versus the context and coverage. Now, in the real world, when we want to make sense of the world, our physical intelligence, in contrast, really works on both. So for example, if I want to make a decision if there is a safety violation happened at this site, I need both of these pieces of information at the same time. I need to know there is a crane nearby, and I need to know this fellow has moved his helmet. So really the context and the detail both matter when I want to be intelligent about physical realities of the world. So in other words, we would want to build models that capture both aspects. They are, give us the long context, but they have multiple resolution and scale when we think about the incidents in there. And in fact, this is how our intelligence in the real physical world works. The problem becomes even more interesting and difficult when you think about dynamics, complexity, spatial complexity, correlation. Here is a simple example where you can see on the one hand, this fellow sort of falling off the beam, but you don't see the context because you're too close. If you squint your eyes after you have seen this detail, you see that the loader is an issue. So in reality, the kind of models and data that we would like to train our intelligence on is this kind of model. It gives me the context, but it also switches where I'm paying attention depending on what is the importance of the information that is being gathered. So in other words, if I was to build the new generation of AI models, I really have to be able to capture both the context as well as the detail. And I need to do this in a dynamic fashion, as we're seeing here. So this is the sort of the gist of why curiosity in the physical world, or ability of moving things around, really matters. In fact, in my research at UCSD, I've spent a ton of time really trying to understand how to build such kind of intelligence out of sensors that are limited and follow the physics of sensing. In a series of papers, in fact, I have shown that it is not possible to achieve and build these models, in fact, achieve these corner points of context and detail at the same time with the existing data if you are passive. If you're sitting there grabbing the data in some arbitrary fashion and you train your models on it, you cannot build physical intelligence in the ways that we really need it. So the next few slides, I'm going to try to convince you how is this kind of research, this kind of proofs work in the world. And I want to emphasize, when we say it's not possible, these are not computational impossibility results, or even the smartness, it's impossible because we couldn't think of it. These are information theoretic impossibility results that basically looks at deficiency in your data and really use that deficiency to justify the impossibility, to prove the impossibility mathematically. So really in the next few slides, I'm going to go a little bit more theoretical and abstract to try to show you the kind of proofs that allow us to prove the kind of results that I just showed. For all of these, I'm going to assume this sequence of events that we just showed in this animation. Basically a large site, many movements and many moving pieces, and really one sequence of events lead to another and ends up in a safety violation. To start with, let me first try to dispel something that nowadays with AI, a lot of people are holding this misunderstanding. Why don't I just train a huge model on the best data that I can collect? So this is sort of my way of saying, let's assume that I have a lot of cameras close by and looking at all of these details in my site, and then I train my model on the aggregate information that is fed in these systems. First thing I want to show is that this is not going to be useful for physically monitoring these systems. So here I'm showing you what happens in classic when you actually try to make sense of the data in a time series fashion. So in a single stream, this is what happens. Your first image is important, then the second image, then the third image, the fourth image, and it's sort of the sequence. For you to be able to here say something bad is going to happen, sort of predict this bad event, you need all of this to be fed to the model as context. You need to know this fellow is holding up something, this fellow is getting too close to the end of the beam, and then potentially this might cause an instability. Right? So this becomes a context, and as I was showing, this is what is the bottleneck of modern AI systems. This long context, the longer you want to hold this information, the more slow the model becomes in predicting. Now what happens when I try to do this for single stream is manageable because I only have one sources of data. Now what happens is if I try to scale my model and try to get feeds from each point in the space, now my context is not only growing with time, but it's also growing with the volume of the space I'm trying to monitor. And as things get, very quickly, these systems choke on the scale that is increasing even in terms of context. So even on the inference time, even if I'm willing to train a large model on minute details of a site, when I try to run it and infer on it, I will quickly hit this sort of bottleneck of context growing very, very rapidly in these systems. So that's the first problem. So I hope with this I have convinced you that if I was to actually build a physically intelligent system, then I need to have models that dynamically decide what resolution matters where in my site. So in other words, the context is used to build models that the resolution sort of dynamically change. So in other words, if I build a information representing the site, the resolution should change with time depending on what we are seeing in the site. And this is the sort of the aim that we have in terms of physical intelligence. We really have to build these systems by embedding the information we know from the sensors collected. And that's exactly the next step of proof that these are not achievable with the kind of passive data that we are learning in the world. Why? This is the technical problem too, is that if you try to build the models with spatially and temporally limited data, the models inherit that limitation in form of blind spots. Let me show you an example. Again, this example, I could take the top view, and of course, I see everything in time, so I have a good temporal resolution. I see everything in time, but because I wanted to cover a whole area, I lost detail or resolution, and that gives me information blind spot in a resolution sense, in a spatial manner. Now, in the previous animations, I focused on one location, let's say here, and I was saying I can look at this detail, but then I will miss the bigger context. You might say, okay, that's pretty silly. Why would you stick with one location? Why don't you think of something smart to do in terms of, even though you're close, maybe you take a really clever trajectory. Is it possible for me to collect data in a clever way from up close such that I learn a model that is good in terms of spatial detail? It turns out that no matter how smart I am, essentially there exists, no matter what trajectory I pick here, there exists one location in the site here, for example, that we will be visiting very rarely. A pigeonhole principle says that you will not see this particular location in the site in time often enough for it to have temporal clarity about the events. So here I have ingested a temporal blind spot by moving my camera. So in other words, if you look at the trade-off of sensing, which was the context or coverage versus resolution, no matter what I do, these information blocks seep in so long as I pick my trajectory in a passive manner, meaning I don't know what is happening in this site, and I just pick a trajectory beforehand. So in other words, in order for me to really solve the problem, I have to go beyond this. So that's the kind of proofs we have. The desired models are dynamic, and we show that if you build models built on coverage, large coverage, you get models that are spatially limited, even though temporally they're pretty good. If you go to high resolution, you will lose temporal information, and you build locally useful information, but you have blind spots temporally. Now this is the way we prove impossibility results. These papers, however, have some good news. And the good news is that it is possible to really push this boundary if we are clever, but not clever in terms of figuring out where to collect information. Clever by saying, I know sensing, I know the physics of sensing, so sensing and intelligence should go hand in hand. So in other words, artificial intelligence needs to be also artificially curious. And that's the key ingredient that my research has brought to the table. And in fact, that is why I have gone ahead and co-founded AI, a startup that really takes this view to build a new model of AI where we take this into account, a model of AI that integrates sensing into the operation. So I kept saying actively taking advantage of the sensing and curiosity, but in order for me to give a better and more clear understanding, really need to understand how humans deal with information deficiencies caused by our sensing, our sensory limitations, and how does curiosity come to save us? So, mechanistically, how does curiosity help us? So this example is my favorite example. I travel a lot and I go to airports. And in airports, this is a classic scenario that there's just lots and lots of events happening. And so when you enter a crowded area with information overload, what we do is we keep the context in mind. This is an airport. It's going to be crowded. So we hone in on target. So I need to get to gate 25, and I walk there, ignoring lots of noise, like baby crying, TSA announcements, and whatnot. I get to the gate, and it has happened to me. You get to the gate, and the gate is unexpectedly empty. That's where you say, I have these sensors that are very, very limited. They have been important in my missing, in the past, noises and sounds. So maybe while that kid was crying, I didn't hear an announcement about a gate change. So your brain falls into this, I'm uncertain about when it happened, so you hypothesize what kind of information you missed, and then you start, after this, to act, to collect information that can actually eliminate the information blind spot that was created because you were looking at the context and not know where the details that mattered was. So you act right away to get the correct data. This could be you go to the board and read what the gate information is. It could be you checking your phone and whatnot, depending on the hypotheses that you have in terms of. So this is what we call curiosity mechanistically. It's the process that moves us besides sitting passively hoping information is processed, the right information is processed for the right decisions and intelligence that I need to do. So this is the key aspect. And this is what we did at AI. We took this curiosity as an embodied function mechanistically and tried to build the new generation of AI systems. So let's review what is mechanistically important. The first thing is that our intelligent systems has to always recognize inconsistency or unfamiliarity with what they were expected to see. And what they expected to see depends on what is the most important and relevant information. And that's what you focus on when you are actually collecting data. When you identify inconsistency between what you're seeing now and what you expected to see, then you go into conceptualizing possible observations that you didn't take because you were distracted, your sensors were not good. So conceptualize, if I had done this, if I had paid more attention to the TSA announcement, I would have collected observations that right now you're missing. So you conceptualize this, you postulate hypotheses about which piece of information you lost because of what, and then identify the suitable data that can address this hypothesis. They can test this hypothesis, whether this is correct or not. And then depending on what that source of suitable data is, you get into action mode, you move, you change, where you're looking, the minimum, but you might even walk towards somewhere or go and talk to someone. So that's the active part. So you need this closed loop circle of hypothesizing, testing, and then getting to action to collect data and sense. So this is sort of a full cycle of curiosity. And this is what basically allows us to really take intelligence and really bring it to the physical world, to go to many, many environments where you have large-scale operations with lots and lots of potential sources of information, where you have to hierarchically hypothesize, sense, and make sense of the world. And these are the areas that we have been looking at: oil and gas, energy production, what happens at a port, airport, seaport, the infrastructure for example, large-scale networks and the cyber information they collect, wireless and so on. So we've looked at these, and this is exactly this new models that we have built. We call them curiosity-driven AI for the physical world. So let me pause here and just kind of emphasize. So these new models are going to exactly take the components that we have talked about. And the components were a sort of higher functioning brain-like operation that is processing what we have collected, and then an understanding of where the sources of data is vis-a-vis our sensory inputs, or our ability to collect sensory information, and then also profiling our ability to act upon the needs that we have, the informational needs. And these are exactly the components that we have built into our proprietary technology we call active physical intelligence. So active physical intelligence is a new intelligence system. It's a novel intelligence system that actively and deliberately really focuses the attention of a model, of a large model, on the important data as opposed to misaligned data. The components are multimodal sensing and hypothesis-driven reasoning. And then really what it does, it builds upon advances we are seeing both in terms of connectivity. More and more these days we see a large amount of sensors and sensory devices, from IoT to satellite imagery to cameras that feed data. So that's connectedness, I would say. Embodiment, we are seeing better and better methods to move sensors, robot dogs, drones, and so on top of generative AI, which we all by now is a household name in terms of what we see is happening in the language domain. So we put these advances together and we built this new system. This new system, just like I described the mechanistic process of curiosity, works on building a hypothetical adaptive world model, similar to what I was showing in terms of physical intelligence for the construction sites and safety management. It has some user interface, because we still would like humans to be able to operate and understand this physically intelligent system. But also it has a very integrated process to understand sensors, to profile them, and really feed their data up all the way to the model that builds this hypothesis world. And really, you can sort of think of this as a control platform that closes the loop and really brings this full cycle of curiosity into life. So in terms of the foundation model, or the large model that we are building really integrates the ability to collect information from multiple sensors, and these multiple sensors as we have seen in our example, can be mobile, can be controllable with small variation. You can zoom or pan out a camera, and this is really our active data and inference allows us to really consume this data in an active fashion. And then build these foundation models that are multi-resolution and adaptive, as we saw. So the models are going to be built on this active data and inference and active foundation model. These are the two components of active physical intelligence from a conceptual perspective. And I'm going to show you an example in the visual domain prototype to how this looks like. So here I'm showing you the sports field at UCSD where we collected data. And for the first time, we show that you can take a video from this field and you ask counterfactual questions. So this is our adaptive model adapts to what you need to know rather than the information that you have fed it. So here, the closest model out there, world model out there that you can do this kind of work with is the model built in NVIDIA recently called Gen 3C. This is a video generation model that you can pose question to it. So you give it a video and you can ask it, what happens if I move the camera? In this world, what would I have seen? And again, remember that we want this model to be multi-resolution and really change the prediction depending on what is important. So here, let's assume you're helping the team that makes the videography for the game. And ahead of time, they have decided, and this is in fact what you're seeing in this video that I was showing you. So this is a video that they have collected, let's say, from a drone. And they want to know, is this a good angle for the videography that they will have to do when the players are are playing? So we are asking, okay, if I move the camera or the drone closer to this goalpost, what would I see? Will I keep the details of the far distance? Will I be able to see how the coaches are moving? What do I see about the ball? And in particular, if I get closer to the goalpost, will I be able to see where the ball is and does it cross the right, with the right distance and so on and so forth. We give this question to Gen 3C. Say basically a simple question. What would you have captured if instead of hovering where we did hover, if we had hovered closer to the goalpost? And let's see what Gen 3C's response is. So Gen 3C says, hover near the goalpost. And what it produces is this video. And as you can see, it really is not able to capture any sense of what the world would have looked like. Everything morphs and gets kind of convoluted. Our model, on the other hand, sort of imagines if I were closer, I would see this drone this way, and this is the goalpost. So it has an imagination world that keeps the details and brings the details into really the focus. And this is where it's very different from the world models out there. It keeps the context. Here's I'm showing now that data was collected at UCSD's campus. This is the data that is from fixed data sets, the benchmark data sets collected by Waymo in San Francisco. And as you can see, this is a kind of a question that an autonomous driving scenario would be interested in. Say you have this first video, which is is collected from the cameras mounted on top of the car, but the car here gets to the crosswalk and stops. And we all do this sort of counterfactual questioning of ourselves. What would happen if I didn't have to wait on the crosswalk? If I could quickly pass this cross section, what would I see? Can I see the detail in that square? Is that square crowded? And if it is, maybe I should turn right? So this kind of questioning becomes really important. And so you want to say, what if I get close to the square? Can I actually focus? Again, we ask this question to Gen 3C, and it produces this almost still image. It's as if you just ask it, can you show me the square? And it sort of produced a blow up of one frame of all of your video. It does not have detail. It does not answer the question, should I avoid the traffic in the square or whatnot? We pose the same question to our model. We ask, what will I see if I was zooming in? And now, as you can see, I have dynamics, I have detail, I have imagined the world with much far more detail and context than the other models. Do the same thing. Instead of drive closer, I asked, no, you know what? I want to be even better than that. If I imagined that I had a camera installed near the square, and that camera is feeding information to me, so I didn't have to waste any time, any frames of my video getting close, again, what would I have seen? Again, if you pose the same question, but the same video as the initial feed to the world model, and say, can you give me the details in the square? Again, Gen 3C, the state-of-the-art model out there, sort of gives you very little information, and in fact does not take the context of the long video into account very well. In contrast, our model sort of gets you really close, and it sort of tries to balance the detail of the construction and structure behind the square with the details of moving and the context of movement in the square. So again, this is the kind of models that you will only be able to build if you have this active data and active, curious, so you take your context and you really cook up what data matters. This is another example. Again, a car is going and you are asking this counterfactual question, would I be able to see the details around the parking lot? Again, you pose it to the classic, to the state of the art, and it just kind of warps up, doesn't answer your question, while our model can beautifully give you the detail that you're asking. So in this set of examples, now I'm going to try to use the model for counterfactual reasoning in time. So far, all the examples were what happens if I move the camera, if I was viewing it from a different point of view. Now I'm going to ask the question, what if temporally I had sensing happen at a different time? So here on the left-hand side, I have a very short clip that after which the camera has been shut off. And I ask my models to predict what would have happened had I not had this camera shut down, right? So in other words, if I had let it roll, what else could I have seen? Right? And so this is really asking fast forward in time, even though the context I'm giving you is this short video, fast forward it and tell me what are the possible or plausible futures. Again, when we compare ourselves to Gen 3C, Gen 3C loses the context very fast, as opposed to our scenario that sort of tries to take the information that it had from the original context and fast forward it as much as it can by taking the context that this is a street with people in it and actively imagine a detailed resolution into the future. This test, we go backward in time. So now, again, I have a really short video, and I want to know what are the possible explanations as where that person came from. Again, if you pass it to Gen 3C, Gen 3C does not do a very good job. Everything warps up, as opposed to our model, which imagines the person walking from the right side of the image and come back. So this is to just show you what is the benefit of actively managing your data if you're building world models, if you're building these adaptive world models that can capture context and resolution. One thing that I didn't talk about, this was all visual data, is that you can do this with multiple modalities of sensing, with multiple functionalities, and really bring everything together for real-time adaptive decision making. And this is what we do in the real world. So the real world, the real world problem that we are focusing at COV AI is the problem of unplanned shutdowns. And this is the problem that I feel very strongly about. Really, human beings, we have built these expensive, complicated, technological, large-scale world that we are not able to monitor sufficiently well. We lose track of the details and the context. And that means we lose money, we damage environment in an irreversible fashion, and even there are some loss of life involved. So in this world, physical intelligence would mean that I should be able to monitor these infrastructure and these large-scale systems much better. And that's a problem that we have focused. We have done 2 projects already with EnergySight. We have built a hardware-agnostic models that very much like the models I talked about, the world models I talk about in the visual domain, but now these are going to take multiplicity of data. Here I am showing visual data as well as thermal data and putting them together to really reduce your blind spots in energy sites, petrochemical facilities, and refineries in terms of both cost but also impact. Here's the demo. The demo is really simple. This is the app as it's observed by our customers. They can go to the organization, take their data. Their data consists of many, many components, from publicly available data that you can get from, like, say, Google Earth or whatnot, all the way to the gallery of the data that you have collected. The capabilities are, it's the first active AI in the sense that it actually actively orchestrates the data, provide some key points as what are the important points of views for any understanding. It allows the user to investigate the source of shortcomings in terms of their data, the possible anomalies that they can do. It allows a deeper attention to be paid to little details, even though the scale and the context remains quite large. And then this allows us to really think about faster decision-making for predictive maintenance, as well as an interactive, active AI-assisted discussion with the data sets. So this allows us to do continuously deep analysis of the data of the site, make recommendations, and then also bring the attention of the user to where the data is signaling needing to be complemented, and then also potentially actionable insight. We have looked at energy. This is not limited to energy. The kind of problems we are solving really have meaningful implication for the way airports and seaports work, the way manufacturing and large-scale manufacturing sites work, and so on and so forth. So really, I hope, in summary, I've convinced you that the next generation of AI systems will have to be curious, will have to intelligently and actively pay attention to the details that matter at the resolution within the context that matters. The components that will make this possible is we need to be taking the limitations of our hardware and sensing into account without depending on them or without relying on them to always be there. So we really need to be, in an agnostic manner, integrate the sensing, and this sensing has to be multimodal, and then build from that a set of hypotheses around the sources of data as well as the intelligence. Again, this would not be possible without the advances that we're seeing in connected AI, embodied AI, and generative AI. And really, we are really well positioned for the first time to bring this first artificial curiosity platform to the real world. So I'm going to stop here. I want to do a shout out to all my brilliant graduate students, postdoc, and collaborators at UCSD, which made the first part of the talk possible. This questions, abstract questions around limitations of building intelligence on passive data. And then also do a shout out to my really dream team at my startup Cov AI, who have really taken this ambitious out there idea and really have helped me build a whole system around it. With that, I will conclude the talk.